Have you ever wondered how does Netflix recommend movies? How does YouTube predict what you'll watch next? And how can a machine learn patterns from data? Today, we're going to learn one of the most important foundations of machine learning, linear regression. But we're not stopping at just fitting a line. We'll also derive the mathematics behind how machines actually learn using cost functions, partial differentiation, chain rule, and gradient descent. We'll even visualize gradient descent in 3D so you can finally see what's happening mathematically. So what is machine learning? So machine learning is the process of allowing computers to learn patterns from data instead of explicitly programming every rule. So suppose we have this data set. So this column shows the hours studied and the exam scores, so their corresponding exam scores. It shows here that, for example, 1 hour of study session resulted to an exam score of 50, 2 resulted to 55, and so on. So this is called supervised learning. So supervised learning because we already know the correct answers and we train the model using labeled examples. For example, the exam scores. One of the simplest supervised learning algorithm is linear regression. Linear regression tries to fit the best straight line through data. The equation is f of x is equal to mx plus b. But sometimes f of x is just referred to as y hat. So for this video, I'll probably be interchangeably referring to these two as the predicted output. Then x is equal to the input, m is equal to the slope, then b for the intercept. I'll be going over this in detail in just a few, but basically the machine's goal is to find the best value of m and b that produce the best predictions. But what does best actually means? So as I've mentioned earlier, m is equals to the slope and b is equals to the intercept. Well, actually, to be clear, this should be the y-intercept. So this just means that what is the value of y when x is equal to 0. So to do that, we can do it graphically by just extending the model or the line up to the y-axis. So at this point, x is equals to 0, and as we can see, when x is equals to 0, y is approximately, let's say, 41.5. Yeah, let's approximately 41.5. So let's just say b is equals to 41.5. And then to get m or the slope, so m, the formula for m is uh, yi minus yi minus 1 over xi minus xi minus 1. So we just pick 2 points actually. Then for example, we chose this one and this one. So to compute that, we just input the value. So yi is about 71 minus yi minus 1 is approximately, by the way, we're pertaining to the value of the predictions using this line. So we're using the y values using this line, not the actual points. So for yi minus 1, that is approximately about 63 over xi 4 minus xi minus 1, which is 3, which will give us 8. So m is 8. So the uh, our equation of the line is, or our model is, f of xi is equals to 8xi plus 41.5. So this is just the approximate value of m and b. So what I did is I just solved it graphically and analytically, but there are other methods to solve this. And some predictions will be too high or too low. So we need a single number that measures the total error of the model. That's where the cost function comes in. Next, we move on to cost function. I think I forgot to write this earlier, but what I mentioned here, the gap between the line or the model and the actual y data or the exam score is called the residual, which should be y hat minus the actual y value is equal to the residual, or y hat could also be called f of xi. Now, the most common cost function for linear regression is the mean squared error, which is c as a function of m and b is equal to 1 over 2n multiplied by the sum from I is equals to 1 to n of the square of the residual. I think I'll just write this as f of xi minus yi, or the actual y values, squared. Now, substituting the linear regression equation, we have where c as a function of m and b is equal to the cost function or the mean squared error, and n is equal to the number of samples or points. Now, let's break this down. So, why square the error? Uh, you might be actually wondering why there is an 2 right here. So I think in some books you won't see this value of 2, but uh, this is purely for mathematical convenience because I will be deriving the this cost function later. So Why square the error? Because so that negative and positive errors won't cancel, and so that larger mistakes are penalized more heavily. Now let's visualize the cost function. Suppose we have another function, a different function than the previous one. F of xi is equal to mxi plus b. So the cost function depends on m and b. So that means for every combination of parameters, there's a corresponding cost. And if we plot those parameters, we get a 3D bowl-shaped surface. So I'll just paste this curve right here. Suppose this is the curve I'm talking about. So let's suppose the z-axis as the cost function, the y-axis as the b parameter, and the x-axis as the m. So the bottom of the bowl represents the minimum cost, and that means the best fitting line. So suppose this is the bottom of the bowl. So that means, apologies for my drawing, the best combination of B and M is, for B, that's about -3, and for M, let's just approximate it to -3 also. So this is just an estimate. So we have f of xi is equal to -3xi minus 3 then. So this is the best fitting line for the particular function. Now, so how does the machine find the bottom of the bowl? So this is done through gradient descent. Imagine that you're standing on this any point on this curve, and you are blindfolded, and to reach the bottom, you feel which direction slopes downward the most, then take a small step. Suppose you're standing here, and um, let's suppose that this curve is not is uneven. It has an uneven surface. So you feel which direction slopes downward the most. Then eventually, every step you take, slowly but surely, you will reach the bottom of the bowl. Repeat this enough times and you will eventually reach the minimum. That's exactly what gradient descent does mathematically. Okay, so to know which direction goes downhill, we need derivatives. A derivative measures slope, but now we have multiple variables, m and b. So we use partial derivatives. Now, this topic is not about derivatives, but if you want a separate lesson about that, please let me know in the comments and we can have a separate video. But partial derivatives, these measure how the cost changes with respect to one variable at a time. So we need the partial derivative of the cost function with respect to m, and the cost function, sorry, I mean the partial derivative of the cost function with respect to b. Okay, so now we move on to deriving the partial derivatives of the cost function with respect to m and b. So, but first, we must recall that in partial derivative, for example, this one, the partial derivative of the cost function with respect to m, so we should just differentiate the function with respect to m and treat other variables such as b, xi, and yi as constants. Then we also need to recall the chain rule. So this just shows that to differentiate a function inside another function, so we just bring down the exponent, multiply to the inner function, then subtract 1 from the exponent, then multiply that by the derivative of the inner function. That's why we got f prime of x, and we just apply it here. But first, we must plug in the linear regression equation to f of xi. So that's why we have m of xi plus b minus yi. So please do not be worried about this summation sign here, or summation symbol here, because if we break that down, we would just be left with a very long function, and if we derive this, we would just differentiate each term individually. So it would be simpler if we just show this summation symbol overall. So start off, as you can remember what I told you earlier, we should bring down this exponent 2. So that's why we have 2 here. Then multiply it uh, with the inner function, this one right here. So we just copy it, and then we multiply that to the derivative of the inner function right here. So since we're differentiating with respect to m, we would treat this xi, b, and yi as constant. So the derivative of mxi, so since uh, xi is a constant and differentiating by m, we will just be left with xi. Then since b is constant, this would be 0. Y constant, this would be 0 as well. So to simplify, we would just be left with this function. Then same goes for the partial derivative of the cost function with respect to b. This would be much more simple. Again, we start with the cost function, plug in the linear regression equation. So we bring down 2, then multiply it to the inner function right here. Just copy it. Uh, Sorry, I forgot. As I mentioned earlier, we wrote 2 here for convenience so that it would cancel out. So then we now multiply with the inner function, which is right here. So as mentioned earlier, with respect to b, so all other variables such as m, xi, and yi would be constants. Since these two are constant, differentiating it would be 0. The derivative of b would be 1 minus the derivative of y, which is constant. So this should be 0. And we are left with 1. So we multiply that overall with just 1, which is much simpler than multiplying with xi using the partial derivative of the cost function with respect to m. So we would just be left with this function right here. Then just plugging in the f of xi for the linear regression equation. So we have now derived the partial derivatives of the cost function with respect to m and b. Okay, so now we move on to the gradient descent algorithm. So suppose we have this simple cost function with respect to m, and its relationship with the variable m is represented by a bowl shape or a parabolic shape, and this is the minimum. And then for gradient descent, remember we pick a point, for example here m is equals to 1, then we update it here, moves here, then here, closer and closer to the minimum value, the cost function in particular, which corresponds to the optimal value of the m parameter. But how do we know the next value of m? So we just use this equation uh, think we've already encountered this, but for this symbol right here, alpha, this is called the learning rate, but in some books, this is step size, or also in my university year, uh, fun fact, I actually graduated with a degree in chemical engineering. Then for the gradient descent algorithm, we do a simultaneous update of the m and b parameter. So the new value of m is represented by this here, tmp underscore m, or temporary m. Same goes for b, temporary b. So for the gradient descent algorithm, we initialize starting values for the variables. So suppose we start with m is equals to 0, b is equals to 0, and the alpha is equals to, like, for example, 0.1. Because the value of alpha is typically in the range of 0 to 1. So we pick the optimal value, which is in the range of 0 to 1. So this is important. We want to pick a value for alpha, so because this controls the how fast or how large we update our parameter. We want to pick a value that is not so small, or not so large, because for example, if it's too small, so the value would move very slow till it reach the minimum. And if it's too large, it might not even reach the minimum at all. So, as we call it, it's diverging. And when we reach the minimum, it's converging. So, first, we substitute these partial derivatives with the ones we derived earlier. So, I think it would be more appropriate to use this form. So, we plug the values of m, b, and alpha for both equations. That's how we update the m and b parameters. So we now have the new values of m and b. So how do we know when to stop using the update rule? So we would typically stop when we notice that m and b is not changing that much anymore. For example, it's only changing very, very small, up to the maybe fourth decimal value. I think that would be okay depending on the situation and how precise you want to be. But that's typically how you would end the gradient descent algorithm, which means that you finally reach the optimal value for m and b that corresponds to the minimum cost function. So to recap, today we learned what machine learning is, how linear regression works, what cost functions do, partial derivatives, chain rule, and how gradient descent learns parameters. So at its core, machine learning is optimization using data, and gradient descent is one of the most important optimization algorithms ever created. If you enjoyed this video and want more deep dives into machine learning, mathematics, subscribe and let me know what topic you want next.